So it is pretty common to have questions, certainly about oppositely charged parallel plates. Ooh, you know what I should do? Let's take these and do, whoops. And make them, sure, like that. And then let's do this. Yeah. And then let's say there's a charge here. Nope, not positive. Let's call it a negative charge. And let's say that there's some potential difference between those plates. And this thing is released from rest. And it has some mass, we'll call it N. Well, what's this charge going to do? This object going to do? One word. Accelerate. And it's going to accelerate constantly because there is a field between these plates that looks like what? It goes this way. Actually made an inadvertent smart choice here. If you're to draw these these electric field lines, which rare, I think, on the AP, but very common on the Regents exam, make the lines touch the plates. Okay? Now, talk to me about this field. Robbie? Yeah, this is uniform, which means?
Everywhere between the two plates feel the same force.
Yeah. So this field is the same exact strength everywhere, which means the force on the charge, if we put the charge here, or, whoops, I made it positive. Well, it's okay, I can make a charge positive. So these charges, these positive charges, would feel forces that point this way, F, 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 that are all the same exact strength. That's what a uniform field does. It exerts the same exact force no matter where you are. Okay? This one happens to be a negative charge. And the definition of the direction of electric fields is that they point in the direction of the force that a positive charge would experience. These are negative charges, so they're pushed in the direction opposite the one that the field points. So there's FE. So eventually this thing gets to here and is now moving at some speed v. Let's talk about how we can find that speed v. This is a common one. So we could do this, right? That the net force is ma. And the net force is QE is ma. We could find the acceleration as QE over m. Not at all an unlikely, not at all an uncommon thing to have to do. Now, if we wanted to find the speed v, we'd have to know something else, right? We'd probably have to know how far apart these plates were. So let's say we knew that. If we know that these are a distance, let's call d apart, well, then we could probably do some kinematic stuff, right? And say that v squared is v naught squared plus 2a delta x. We could ditch that. And we could say that v is the square root of 2a delta x. this is going to work out pretty neat in a minute. Wait for it. Now, there's a different way to find the final speed of this thing. Because we can find it without knowing how... Notice, we did this without knowing the potential difference between the plates. We can also do it without knowing the distance, but knowing the potential difference. You know how to do that way? Very good, because you are really saying, Sarah said Q delta V is 1/2 mv squared, because you are really saying that what? So this is sort of method 1. Method 2, hang on, let me move method 1 over here. Let's get out of there. Method 2, we're saying that work changes energy. The work done by the field is Q delta V. And this is KE final minus KE initial, where KE initial is 0. Q delta V is 1/2 mv squared. So this says that V is the square root of 2Q delta V over M. What about those two expressions says the same thing? What is it, Sierra? Right, we said a minute ago that electric field can be measured in volts per meter. Right, here's our ED, and there's our ED. The rest is the same. Maybe even method 3, right? That's method 2.5 is still doing this. What's another way to write work? Force times distance. So we could say that work is FED equals 1/2 mv squared, and FE is QE. And that leads us again to the same thing we got there, right? To QED over M. Yeah, no matter what, we get to the same spot. Yes.
Isn't there also one that's like E equals V over D?
Yeah, that would be this, right? V is, no, there's no V is E over D. Okay, okay. That's a different one, and we'll get to that too. Now let's take this whole thing. Let's take this whole thing. I'm going to move this whole dealie to a new page group. And then let's copy. Let's go over here. Let's say now that as this thing fires out of here, it enters a field, a uniform magnetic field that looks like this. What's this thing do now? You're going lefty, this negative charge. I go lefty, negative charge. So left thumb to the right, field that points out, right? Because the dots mean the arrow's coming at you. So this thing, I know, Sierra, it's bad. So if you're like Sierra and don't have a left hand, right, you just use the right hand and then take the opposite of your answer. Right, but this thing is going to be pushed, well, at this instant, it's going to be pushed up. But then when it starts moving up, the velocity vector changes, but in general, what's this thing always end up doing? Moving in a circular path that is going to look, I should be a little more careful about these. We'll say the field is really right all the way there. So immediately, never mind that. Let's do this. Sure. So this thing would move out to here, and then once it enters the field, start to move in a circular path like that. And it'll move in a circular path of radius r. Where out here, if we do a net force equals ma, what's the force? It's a magnetic force. And how do we quantify that magnetic force? QVB. And the acceleration is v squared over r. So we can write this as QB equals mv over r. Just ditched that and that. We can write the radius of this circular path, if we wanted to, if we were asked to, as mv over qb. You can take v from the last pages, whatever it was. Okay? This part by itself, very, very common. All right?
Does it keep like going in a circle?
Great question. Would this thing ever go in a circle? The most it could ever do is move in a half circle. Because if it were to go in a circle, that means it would have to get in the field and then start turning to get into a circle. And it can't get in the field without turning. So immediately, right, notice, so right here is where it enters the field. Immediately it starts turning. So there's no way it could ever get into a circle without changing its radius.
What happens if it's spontaneous, like the more field has?
Well, sure. So if this were, if this were a field made by, I don't know, say a big single, North Pole like that, the field strength decreases as we get away from this. It's not really what I wanted like that. But yeah, if it were a non-uniform field, all hell breaks loose, right? But we don't do those problems. All right, we deal only with constant magnetic field. That you'll have to do next year with cons. Okay? Yes?
Do we ever have a electric field that wasn't uniform?
Sure. We okay with this one? I'll cut this one and go to something else.